Okay, we're in the same exact file as yesterday. It's still called 8.1 Intro to Logs. This is day 2, and this is right in the middle of our slide deck. I would say on mine it's like the 12th slide, but it's very possibly different on yours. In fact, I'm pretty sure it's different on yours because I have some pages that you don't at the beginning of test slides. So it's probably like slide 8-ish. Anyway, wherever it is, find this slide, and this is about the graphs of logs and exponents. So I was going to show you, this is a log graph. That is y equals log base 10 of x. Now, if I make it a different base, that's really the only thing you could do if you're going to graph this with an x right here in the argument spot. In case you forgot, that's called the argument. This is called the base. If I make that base different, let's just put one more on this same little set of notes for you. It would go through the same spot right here. I'll explain why in a second. But it would go higher than that, because pretty much the biggest base we ever practically see is base 10. A lot of times you will see one that's a base, well, 2, log base 3, 4, 5, 6, 7, 8, 9, 10. But there's one special one. Do you remember? It's a letter. Log base E. And really, E, again, these are a lot of little things you should know. This is about 2.7. It's 2.718, but that's about 3, isn't it? I mean, 2.718 is pretty much 2.3. Or, sorry, it's pretty much 3. So it's pretty much a log base 3. What's the difference? Think for a second about what this means. That's x, that's y. Y is x. If x equals 1, this is the spot where x equals 1. Why is that graph, both of them are going through that spot? Because if x equals 1, there's some special properties involved. All right, I want to back up for a second. Just try to remember this about logs. That they look, and this is a dumb way to remember it, but it might work for you. Imagine that's a tree, and then you have some serious wind. Why is it going into the ground? Because it has roots, right? These are like the roots. And then it stays in the ground at that spot, right? When it bends over in the big wind, and there's a huge wind this way, and they're blowing over like this. So think about it. A log is just a tree that's been blown over in the wind, right? Yeah? All right, however you want to remember it, that's what the log parent graphs look like. And I was trying to explain why they always go through this spot, because that's a 1, and why does that matter? Because, watch this, log base 3 of 1 equals, well, you may remember, I know this has been a weekend, so your brain's probably hasn't done this in a while, but if there is no variable, then I should put 1. What does it equal? X. And then the most important thing about Friday was that you learned to rewrite these puppies. To solve this, I should rewrite it. That's 3, not to the 1, it's 3 to the x equals 1, and I want you to just think that through. 3 to the what equals 1? 0. What does that show you? It shows you that when there's a 1 right here, the answer is 0. Like, even if the base was different, let's say the base was log base, so how about E, which is 2.718 of 1? Do you get, I would end up writing 2.718 to the x equals 1, and if it has to be equal to 1, that has to be what? 0. So, when there's a 1 in the argument spot, you get nothing. You get 0. You get an answer of 0. So, log base 4 of 1. And you got to be able to just go, oh, that one's 0. There's a 1 in the argument. I have a dumb way of remembering this, too. If you win the argument, you get nothing. It's really true in life a lot of times, too. I have had a lot of pointless arguments with either friends or my wife, and even if I win the argument and I have belittled the other person, I got nothing out of winning then. You know what I mean? Like, let's say my wife doesn't understand what USB, the latest USB 3 port is, and she thinks it's the same as the other. Well, it's still USB either way, it's the same thing. And I'm like, no, it's not the same thing. USB 3 is like 10 times faster and blah, 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 blah. And then, so what if I'm right? I can win this argument and I get nothing. In fact, it's actually probably worse than that, because now I won the argument, but now I'm the bad guy for being so mean about it. So anyway, if you've won the argument, you get nothing. Try not to get into arguments over dumb things, or you'll just get nothing. All right, so here's the one. Log base q of 1 equals m, and it's on the ACT test. What answer are you looking for? I changed it up a little bit, but come on, we can do this. What would they have in the A, B, C, D? What could you tell about this thing? Come on. Yes, sir. M equals 0. You'd be looking for the one that's at M equals 0. That's the one. Because if you've got a 1 in the argument, you'll get a 0 there. Now that you see it, it's probably like, oh yeah, that's pretty obvious. But only one person figured it out. Okay, so that's a good ACT type question. It doesn't just hit you right off the bat, but then if you know the system, you know what logs mean, you could even go like this. A to the m equals 1, and then you got to think it through and go, okay, well, either, what's a possibility? A could be 0, but that's another thing I'm going to teach you today is some of the little exceptions to logs. You can't have a 0 base. Not allowed. And if you can't have a 0 base, the only way to make this thing equal 1, well, even if this was a 0 base, that wouldn't have made it equal 1 anyway. That was dumb. But still something I got to talk about. The only way to make this thing 1 would be to make the m 0. Okay. So what are the rules about the logs? I'm going to give you this log base b. We'll use b for the base. That makes sense, right? And what letter do you think I'm going to use for the next part? Since it's called the argument, I might use the A, okay, is equal to, let's say, C. I could have used any letters. I'm just trying to be smart about picking letters. The B for the base, A for the argument. C is probably a bad choice. What would have been better? E for exponent, but why should I never use E? Because E's not supposed to be a variable. E's supposed to be 2.718, that special number. All right. So anyway, could you get the door for us, please? So he's got it. He's got it. Thank you. All right. Here's the rules. B must be greater than 0. And there's one more thing you probably wouldn't expect. And that's that B cannot equal 1. Why can't you have a base of 1? Well, I want you to think about that for a second. Log base 1 of 4, solve it for me once. If I use a base of 1, just see what happens. What's happening? So tell me the equation you got when you, or first of all, what did you put here? Good, and then, yeah, you can't make 1 turn into 4. You might think if you put the right thing here, you could, but think about it. If you put a 2 there, it's still 1. 1 to the second is still 1, right? You can't make it work. Therefore, the base cannot be 1. Not allowed to have a base of 1. We just showed you why it could fail. And math doesn't like to have any possibilities of something being undefined. All right. So next up, the rules about A. A is simpler. A just needs to be greater than 0. The argument cannot be negative and it cannot be 0. You're drifting. You're too warm. I know. This room's too warm. Make some notes. It'll help. I don't know what they have done in this room to make it so warm today. And pause for a second. Okay, so if A is greater than 0, then so far I'm legal. Like, this has got to be bigger than 0 and can't be 1. This has got to be a number that's bigger than 0. And a special one is that if it is 1, then I know this answer. This has to be 0, but that's a different rule. All right, and last but not least, the C, which could be E for exponent, except you don't want to use E for a variable. And C just has to be an element of R. What the heck does that mean? Think about it. Yes? Has to be a real number. Do you get there's a lot of real numbers? Because that's the exponent. And do you get exponents in this? A lot of times they're fraction exponents. All right. So we can have fractions. We can even have negatives. You can have negative exponents. We do that a lot too. All right, 2-second reminder on fraction exponents. Do that one in your head. Figure out the answer. Write it down. This is a hard enough lesson. I want you to have somebody to check with and work on some of these problems together. So I'm going to group you up right now. I'm going to stop while I do that. Okay, so here's a... I stopped the recording for a second, so I'm not sure exactly what I lost there, but only a minute or two. I was just reminding people about these fraction exponents here. We did 27 to the 2/3 power, and that one came out to 9. And then I said, what if we had put it to a negative power? 9 to the negative 1. It just puts 1 over the answer, 1/9. All right, so just a couple seconds on doing fraction and negative exponents. That comes up a lot in logs. Okay, now we got a bunch of properties to know. I'll get back to the graphs in a little bit, but you need to know these properties, one of which was I just taught you that if you have log base 3 of 1, log base does not matter. If there's a 1 there, you've won the argument and you get nothing, 0. Can you work it out the slow way and put an x here? Yeah, you can do all these properties I'm about to show you the slow way and say 3 to the x equals 1 and then puzzle it and go 3 to the what is 1? Oh yeah, 3 to the 0 is 1. I can get x equals 0. It's just you should be able to do them a lot faster than that. All right, here's another property that I'd say is the one that comes up more than any other one. It's a what does this kind equal? Well, hint, that 9 could be written as a 3 squared. Why would that be smart? This is something to start to look for, is that's the base of this log. That's the base of the argument. Do you get that the bases are the same? If the bases are the same, then your answer's already there. What is the answer to this? It's 2. Now, could you solve it by going the long way, saying equals x, 3 to the x equals 3 to the 2. These mean that the tops, the exponents have to be equal, x equals 2. Yeah, but it went way faster. If you just recognize that, answer's 2. I do not, this is rare, do not need you to show work on that. In fact, I kind of hope you're just going to be able to go, oh, that equals 2. All right? Because the problem might be this complicated. It might be 8 to the power of all that. And you got to be able to go, oh, so you mean 8 to the power of 2, which would be 64. See what I mean? Because this part right here is really just 2. All right, let's see if you really caught that. 5 to the log base 5 of 25. A little property I just showed you a second ago should be able to go, oh, boom, boom. Write down what you think the answer is. Compare it with your partner. I'll pause for a second. Let me give that a try. You are correct, sir. How'd you do it?
Log base 5.
That's 2. And I'm glad you're just saying it's 2. But if you had to explain it to somebody, how could you change the 25 to help them see it? Yes. Notice I've made the bases the same. All right. Here's another instance of make the base the same. 8 to the x equals 16 to the 3x. Ew. Well, make the bases the same, then they'll be able to cancel, and the exponents will be equal. Hint, you don't want to try to make them have a base of 4, because that won't work. But you could make them both have a base of 2. I'll pause for a second and give that a try. Okay, this 8 is really 2 to the 3rd. And then I got to put it to the x. This 16 is really 2 to the y. To what? The 4th. And then I got to put it to the 3x. Do you get what just happened there? These are the same as each other. I just swapped out a 2 to the 3rd for an 8. This is the same as each other. I just swapped out a 2 to the 4th for a 16. And the beauty of it is, now technically, I want you to know this. Technically, you don't technically say that you cancel those. I'm not going to be grading you on that, but I want you to know it. Technically, those don't cancel. It's just that this has to equal that. It's faster to cancel them and make it, but technically it's not right. So anyway, 3x equals 4 times 3x, because that's what you do when it's a power to a power, is you times them, right? So that makes 4 times 3x. So I could say 3x is equal to 12x, and then I could divide this down, and don't worry, I know it's a little weird, but let's keep work going here. Minus 3x, minus 3x, and I get 0 equals 9x. What? Did I do something wrong? No, I didn't. What's the answer? X equals what? 0. Now, how can I know if I did that right? I go back to the original problem and see if it actually works. See if x equals 0 works back in here. If I put them both to the 0 power, would they really be equal to each other? Yes, they would. I know that got weird there, but it's important for you to be confident in yourself that, no, I can solve that. That doesn't mean that there's something broken. 9 times what equals 0? 9 times 0 equals 0. Or divide by 9 if that makes you feel better. 0 divided by 9 is 0. And then if you got an answer, and this is important on your next test, there are going to be times when you get an answer that doesn't work. What's that called? Extraneous. You get an answer and you think it's all right and you're confident you did it right. If you really, really want to, if you care, if you really care about that grade on the test, check it, take it, stick it back in, find out if it worked. You know it works if when you stick it in, it actually makes a true statement. Is this really equal? Yeah, it is, and therefore it worked. If it doesn't work, you could have done everything right, and it still might not work. What does that mean? That means that there just isn't any solutions to that problem. Or another way to say it that's a little more nuanced but more correct is to say that the only answer that there was extraneous. In other words, there's no solutions, but if all the kid said is no solutions, I mark it wrong. You got to find the solution and then show that it's extraneous. So if this 0 hadn't actually worked, you'd have to say 0 is the solution, and then you'd cross it off and say extraneous if you tried it and it didn't actually work. Okay. So much information, I know. It's kind of like a fire hose. But there's a lot to teach you about logs, and we need to do it fairly quickly. All right, so here's a few more properties. There's a page I'd like you to find in your notes that has them all listed, which for people who hate taking notes, this is a big advantage. But I think we need to give an example of each one underneath it. Okay, so if I were you, I'd do the whole zoom in tight thing, and then write a little example underneath of each of these properties so that you'll understand them better. I want to start with number 5, because it's the one I showed you before. That's like this one. Log base 2 of 2 is equal to 1. I want you to think about that. Why would that be true? Because the answer is the exponent on this. And what's the exponent that's on that 2 right now? It's a 1. So what's log base 9 of 9? Yep. If the bases are the same, the answer's already there, but what? It's the power. It's a 1. Okay, so the answer to log base 9 of 9 is 1. If these two are the same thing, the answer is the power, and the power will be a 1. Unless the power is something else. That's this power, or that's this answer right, where is it? This guy. This will be an example where, nope, that's not it. I'm sorry. Where is the other one where it's, maybe they don't even tell you that one. That's probably the best one of them all. Nope, it's not even on your list of properties. I'm going to add it. It's going to be property number 9. And it is that log base 6 of 6 to the x. No, I shouldn't use x. 6 to the m equals, what does it equal? That would equal m. Whatever, as long as these two are the same, the answer is that power. That's a better property than a lot of these. All right, I did tell you that one. What's the dumb saying that goes along with it? If you have won the argument, you get nothing. You get 0. See, there's a 1 in the argument spot, and you get 0. That's like log base 3 of 1 equals 0. Because that's a 1, it has to be 3 to the 0. This to the this will equal 1. Okay. This says no answer. Why? Remember my rules about what the argument and the base could be? What's their argument? 0. If your argument is 0, you can't do that. You're not supposed to do that. That's undefined. The argument's not supposed to be 0, so there'd be no answer to that. Same thing if they'd have said log base a of -2. If either of these numbers are negatives, it's a trap. Star Wars reference there. Except I don't look like a giant lizard. Okay. In the movie, you'd have to know that. Anyway, so back to this kind. I'm going to show you how that kind and this kind work on the next page. It's going to be pretty tough to squeeze those in. Log base 3 of x times y. What's happening here is there's two things being multiplied in the argument. This breaks up into 2 logs. Log base 3 of this and log base 3 of that. What do you think the two this and that are? X and y. But then the question becomes, what happens in between them? Is it still multiply as you would think? No, it's not. Multiply and add kind of go together. You'll see this pattern in other advanced math, that multiply and add kind of often go together. Think about it. If you multiply, or if you add 4 plus 4 plus 4 plus 4 plus 4, doesn't that kind of go with 4 times something? See what I mean? So add and multiply kind of go together. All right. So this breaks up into an add. And then I betcha you'll guess right on this one. Don't even say it. Write what you think that one breaks up into. 2 logs. Hint, that's x divided by y. Log base 3 of x, log base 3 of y, and what do you think I put between them? Division goes with subtract. All right. That's these two properties right here. I'll review them at the end. One last question of each kind to make sure that you got them. All right. This one, let's analyze it. We have A, X, and M, and that means that X has a power on it. The argument has a power of M. And then they rearrange it. And the M goes down in front. M times log base A of X. I'm going to give you an example of that. Now, this isn't as easy as the kind where if the bases are the same, the answer's 2. So, you know what I mean? The bases aren't the same. So it's not quite that simple. Remember that all of these can be solved. These can all be solved by saying equals X and then doing a rewrite. 3 to the X equals 5 to the second, and you can solve them that way. It's painful, but you can solve them if you don't memorize these properties. Okay, I want to set it equal to X and try to figure it out. But back to this. What this is equal to, who caught the property well enough to say what they think the answer should be? The little power that was the power goes where? In front. 2 times log base 3 of 5. Basically, this goes down to the front. There's a reason. I can show you why. I think some of you are probably wondering, why would that be true? Just take the power and slap it in the front? All right, here's how it works. Log base 3, would you agree that 5 squared is really 5 times 5? And then didn't we just have a problem earlier where if it was times, then you could break it into 2 logs? Log base 3 of 5 and log base 3 of 5. And then I could multiply turns into add, right? This is that other property that 2 things multiplied can split up and make 2 separate logs. And now if I actually add these together, look what I get. 2 log base 3 of 5s. And that's what we say it is. So, long story short, if it has a power here, you can, if you want to, put it in front. And it won't be there anymore. It'll be here. All right, that's called the power rule. And this guy, log base A of B, on the very first day when I had you check and see like how these logs worked, I had you put one in a calculator. Do you remember me saying you do log B over log A? If you just take out the base 10 there, do you get that's log B over log A? That's that thing where you can rewrite these. Guys, you taking notes with me? Or are you like looking at funny pictures? Okay, good. With a couple quick touches of your thumb that I noticed there. Yes. All right. Stay with me. All right. So this and this get rearranged, and the B goes on top and the A goes on the bottom. And the base 10 there, log base 10, is kind of assumed. If you didn't just write that, I would have accepted it also. So that's saying if you have this, how do you put it in a calculator? Log 7. Log 7 over log 3. And I didn't write any bases. So what base is it? Base 10. Want to know something weird? Could be any base. Could be base E. Log base E. Do you get that there's an LN button on your calculator that is log base E? That would work. If you really want to blow somebody's mind, could be any base. ACT question. It covers logs. In the advanced part, the most, not just, there's no part. This, one of the advanced problems at the end probably about logs could be this. They would say, this has a base of 3. Rewrite it so it has a base of 1/3. And the trick is to just think, oh, it's log 7 over log 3, but then, oh yeah, Mr. Server actually said that it defaults to base 10, but it could be any base I want. So if the question said, I want it to be base 1/3, you could put a 1/3 in for the base. What if they said, I want it to be base 26? That's a really complicated sounding question. Take this and make it log base 26. It's actually incredibly easy. You just say it's log base 26. Can be any base. The reason is it's a ratio. And granted, when this number gets bigger, its actual little decimal gets smaller, but it gets commensurately smaller down here, so it doesn't matter. Because you're dividing them, it can be any base. All right, so let's see if we really got that. Let's say I had log base 5 of 12, and that's base 5 right now, right? Make it into base 42. Go. Should take you 10 seconds if you understood. Make it into base 42. Here's the start. Log 12 over log 5. And then that's assuming base 10, but you want it to be base 42. 42, 42, also the meaning of life, apparently. Know which movie that's referencing. Hitchhiker's Guide to the Galaxy, that's correct. All right. So, that's how you change bases. That was this one right here explained, and they used base 10, but I just told you that you could use base anything you want. There, now we've covered all those properties. Imagine that our test, or the ACT test, had this on it. What's the answer? Log base negative 3 of 3 squared. Yes. The 2 can go out in front of the log. You're right, but that's not the key to the question. Yes. What can't be negative? The base can't be negative, therefore no solution. You can't have a negative base. Remember that? How the base had to be bigger than 0? All right. Now, how about if I make this positive 3? I say, fine. Okay, I'll make it positive. Now what's the answer? 2. Because if these two are the same, the answer is just the power. If you need proof, I make it equal x. 3 to the x equals 3 squared. And then you go, oh, the base is the same. X equals 2. Okay, next one. Write something equivalent to that. Power goes down to the front. How many of you guys remembered that? Cool, you have a short-term memory. All right. Next. What's the answer? Because the 27 can be rewritten in your head as what to the what, then the answer is what? 3. It's the little power there. All right. What's the answer to that? You won the argument. 0. You get nothing. All right. It's log base 3 of 5 times x. Hint, you want to split it into 2 logs. Log base 3 of 5 and log base 3 of x. And what do I put between them? Yeah, multiply goes with plus. If this had been 5 divided by x, it'd be pretty much the same thing, except this would be minus. Okay, there's a ton of properties. Let's do more with graphing. If you have a medium-term memory because it's the beginning of the hour, what's the graph for log? What's it look like? Can you draw it? Sketch it on your iPad. Don't scroll back to the beginning. Remember the tree blown over in the wind? That's what log is. It has roots. Should you go like that? Awesome. Now, what's the base graph for an exponential? Well, hint, exponentials and logs are inverses, and therefore they're a reflection over that line, and therefore, does that look like exponential growth to you, that green one? It is. This is the graph of e to the x. This one would be the graph of log base e to the x, of x. Sorry. So logs are the ones like a tree blown over in the wind. Exponential growth is like this green one here, and this goes through 1, and so does that. Because if you put anything to the power of let me think. If x is, oh, I get it. If x is 0 for this graph right here, that's the spot where x is 0, and therefore y must equal 1. Because if x is 0, it's e to the 0, and e to the 0 equals 1. That's why this will always go through 1, and this will always go through 1. So there's your base graphs. If I just boil this down to log again, just say, here's my log graph. What happens, do you think, if I like add 1 to it? Where does the whole graph go? Come on. It's just a little shift. If I put a +1 at the end, and I just shift the graph up 1? So this whole thing goes up 1. How about if I want to shift it to the right 1? Then, ooh, sorry, hold on. So mixed up here. If I want to shift it to the right 1, hint, it's not +1. What would shift it to the right 1? -1. That shifts it to the right 1. Then it's not going to go through 1 anymore. It's going to go over here. It'll be going through 2 because I shifted it to the right 1. Once you know the parent graph, it's really not that hard to adjust it. So if I said it's 1, or y equals log base e of x plus 2 minus 7, I could say, where is that? And you'd say, okay, well, I know where the parent is. The parent one looks like this. And then I just got to grab this and move it. What does plus 2 mean? Left 2, and then what does the minus 7 mean? Down 7. Just a rough sketch. All right, let's get your homework. Everybody find on this page right here. So there are a, wait a minute, is this the repeat of that? That's day 1. Sorry, that's what your homework was from day 1. It's like, man, that looked familiar. This would be right 3. This would be up to, ooh, what's a negative do again? A flip, also known as a reflection. That's on the outside. Do you remember it's high-vo, right? Horizontal on the inside, and these things that are on the outside are vertical on outside. So that's a vertical flip. If the ln graph, log base e, kind of looks like that, then this thing would be moved up to and then get flipped. Those are a little bit of a pain, but if you've got a brain that can handle spatial stuff, you can see it'd be the blue one. Flipped. Okay, and then there's those properties we talked through already, and here's day 2. Okay, so I'm going to have you do this first page, which is graphing like a 2 to the x. If you don't remember, I'll remind you, XY chart's your best friend in graphing. It'll graph anything. That's why I told you that at the very beginning of the year. Because 2 to the x, if you're like, I don't know exactly where to put that. Is it like this? I know it's exponential, so it might be like that. Well, exactly where is it? Get some points. Stick in a 0. What do you get? 2 to the 0 is 1. Stick in a 1. 2 squared, or 2 to the 1 is 2. Put in a 2. 2 squared is 4. Put in a 3. 2 to the third is 8. Those are points that are on your graph. Yes, you can just do it that way. It's totally okay. After a while, you get sick of doing it by points, and you might want to know that it just kind of goes like this and then gets moved. That's the original one. And then the one that gets moved is this one. And where did he get moved? Down 1. So you just have to take the original graph and move every point down 1. So like do 1. It's got to be 1 under each spot. So this graph would be just underneath it, basically. All right. Remember, XY charts can solve anything. This one is this graph, which generally looks like this, except it's been flipped on the inside, high-low, horizontal on the inside, vertical on outside. So this has been moved vertically up to, and it's been reflected horizontally. Reflected horizontally means that it's going to go this way, so it goes like that. And then up to means it goes like this. Now, if these were just sketches, that'd be good enough. But what did I tell you can solve everything? XY chart. If I need some exact points, I'm going to stick in numbers and see what happens. I'll put in a x is 0, and I get 3 to the 0, which would be 1, plus 2 is 3. I'd put in a 1. 3 to the negative 1 is 1/3. 2 plus 1/3 is 2 1/3. And then I'd actually graph those points, and you'd find out it's pretty darn close to that blue one. Okay. First page, couple problems there. This problem's doable, just a reminder. Just to be a pain, they put the 8 in front. Do you get that's the same as adding 8 at the end? Okay. This one is more about the graphs. I don't think we need quite this many, though. So let's do, this one's too easy. It's taking a log and just, well, actually, for your first log graph, it's not that bad. Remember, log graphs look like this, generally, sketching-wise. But again, if I was going to make an XY chart to get exact points, you want to just be strategic about what points you put in. I'm doing this one right now. Do you get putting in a 2 is an easy thing to do for x? It's a nice number to pick. Log base 2 of 2. And that's equal to, did you learn anything from the properties? What's log base 2 of 2? 1. What's another nice thing to put in here? You could 1 the argument. Put a 1 in there. Put a 1 right here. Because when you put a 1 in there, what do you get? When you 1 the argument, log base 2 of 1, 0. Next thing, do you get if I put in a 2 squared? That'd be another thing that'd be smart to put in there. So this became log base 2 of 2 squared, which would be what? 2. Because if these two are the same, that's the answer. So I'm going to put in an x is 2 squared, which is also known as 4. And I got a y out of log base 2 of 2 squared is 2. There's some points that are on your graph. All right, now I know. I covered a ton of stuff there. If the test was tomorrow, you'd all fail. I get that. Don't feel like you're a failure if you're like, whoa, that was really hard. There was so much stuff there. But I've covered that by I needed to cover all of that because if you didn't know those properties, you couldn't stick numbers in the XY chart. Okay? And now we have quite a few days to absorb that, learn a little bit more, and then you get tested. Your homework for tonight, let's see. Let's finish it off here. We're going to do 64. Let's skip 66. That's an unlucky number anyways. We'll do 68. Let me see what we should do on this. We're not going to go into finding inverses. You did do that before. I showed you how to solve inverses a couple chapters ago, but it's been a while. So we'll stop at the graphing part. So you can stop at number 68 there. That'll be the last one that you do. Now, one thing that's kind of weird. I had a Dropbox set up because I thought I was going to do all of that on Friday. Yeah, right. I can barely do all of that on Friday and today. So anyway, so what you dropped in the Dropbox already, many of you, just finish the assignment here, and you're just going to re-drop it in the Dropbox completed. You know what I mean? You already did the first part. You don't even have to turn in the first part if you haven't already. Just get it all done because we're just going to grade it as one assignment. And I got to stop doing these where I drop them in the Dropbox and then have to grade them myself because it just kills me on the weekends. So we're going to grade some more in class. But you're still going to drop in the Dropbox, but we're going to grade them in class. Because that way I don't have to grade each of you separately at home. My gosh, that adds up. Holy smokes. I have 150 students. Imagine having to go home and I grade 150 papers a night. Okay, that's all I got for you for today. Have your homework done for tomorrow.